All right, good morning, everyone. So, just to remind you, yesterday we started talking about thin film interference, where again, just remind ourselves we have a incoming incident ray, which again is close to the vertical. So, in this case, the normal line, I is close to 0 degrees. Part of it then is going to be reflected offward. That's what we're going to call ray one. The other part then is going to refract down through, hit down here, and then again, part of it's going to be reflected. The other part's going to be transmitted down through here or refracted. Then this guy's going to reflect back upward. And again, part of that's going to be reflected downward. The other part's going to be refracted outward. All we care about is the refracted portion. So that one's going to come out, which we're going to call ray two. And then it's the interference between these two, which allows us to either see it or not see it, depending on if it's constructive versus destructive interference. And again, as we talked about yesterday, we get a phase shift if we go from low index refraction to high index refraction, we get a phase shift. But if we go from high index refraction to low index refraction, we get no phase shift. So if I have 0 or 2 phase shifts, then we have constructive interference as the usual, and then destructive is the usual. But if we have 1 phase shift, in that case, those two switch. So in this case, what would usually be destructive now becomes constructive, and then vice versa, where both of the times they only depend on the wavelength inside of the second medium, because these two lengths are exactly the same. So the path length difference only depends on the wavelength in the second medium, which is given this way. So we started an example last time, which said that we have the light ray, which is coming in, bounces off where it's coming in air. So this guy has an index refraction of N1 equal to 1. This is then acetone, which has an index refraction of 1.25, and that's sitting on top of glass, which has an index refraction of 1.5. And what we're told in this problem is that we have total constructive interference at 700 nanometers, and we have destructive interference at 600 nanometers, if I remember correctly, which I did. I'm awesome today. Anyways, okay. So from there, we want to use this information then to determine the thickness of our acetone here. So this is what we're doing last time. So as we talked about yesterday, what we know is what? Here we go from low index refraction to high index refraction, which means here there is a phase shift. So I'm going to put a yes on this one. So R1 is phase shifted. Simultaneously, we're going from a low index refraction to a high index refraction. So again, we get a phase shift. So ray 2 is also phase shifted, which means we have 2 phase shifts. So we use the usual definitions in this case. Mm-hmm. So from here, we know that for the constructive interference, we're going to have 2 times the length or the thickness of this guy is equal to n times lambda 2, which means that our thickness will be n times lambda 2 divided by 2, but that's the same thing then as n times lambda divided by 2 times the index refraction of the second medium, or in this case, of my acetone. For the other one, we get pretty much the same thing. So here we're going to get L then is going to be equal to n plus 1/2 now, times the wavelength divided by 2 times the index refraction of the acetone. Now, in this case, we're not told what the n value is, right? So we don't know how many wavelengths these guys are out of phase with each other or in phase with each other, but we don't know how far the one has traveled versus how far the other one is, which means that basically to solve this problem, we just have to choose different n values until eventually these two things match. When they match, that's the thickness, okay? Nice and easy. So all we're going to do is evaluate each one of these guys for different n values. So for example, if I do n is equal to 0, find some chalk that actually works. So if n is equal to 0, this thing is obviously 0, right? Anything multiplied by 0 is 0. Let's use this guy. So I'm going to write that over here. L0 then is equal to 0. Let's do n1. So now let's plug in 1. So I'm simply going to multiply all this stuff here by 1. So in this case, we find that L1 then equals 280 nanometers. That's the thickness of this guy. And it's nanometers because, again, this guy is in nanometers. This is just a constant. This is also a constant, and that's a constant. So nanometers. Right? N2, so let's do this for N2. So N is equal to 2. Plug that in. What we get in this case then is this works out to be 560 nanometers. And let's have funsies for one more. So N is equal to 3. So L3 then is equal to 840 nanometers, and et cetera. Mm-hmm. So let's do that now for the other one. So in this case, again, I'm going to start off at n is equal to 0. So for n is equal to 0, I get L0 then is equal to 120 nanometers. So is any of these numbers 120 nanometers? No, so it's not n is equal to 0. So great. So N1, then we're going to get an L1. This is equal to 360 nanometers. Is anything over here 360? No, so let's keep going. So we're going to N is equal to 2. So L2 then is going to be equal to, according to this, 600 nanometers. So is anything over here 600 nanometers? Again, no. Good. So finally, let's do N is equal to 3. So we get L3 then is equal to 840 nanometers. And is anything over here 840 nanometers? Yes. So in this case, since we finally have two matching ones, so that means that the thickness of my acetone is for N is equal to 3, which means that my thickness then L is equal to simply 840 nanometers. So this is the thickness of my acetone. It's okay. Nice and easy. Not too bad. Right. So let's do one more of our thin film interference here. So where am I looking at this? I think it's this one. Yes. So this says that we have light is incident perpendicularly. So again, pretty much almost 90 degrees, or sorry, I keep saying 90 degrees, 0 degrees on a thin layer of material of, in this case, N2 is equal to 1.6, a thickness of 285 nanometers. So in this case, we do know the thickness. And that lies between two other materials where N1 is equal to 1.55 and N3 is equal to 1.33, i.e. water. And then it is reflected, where it's going to interfere maximally, which basically just means constructive interference. And it wants us to know what is the wavelength of the wave in the visible light spectrum. So let's look at this problem. So in this case, get rid of this here. So we know that N1 is equal to what? 1.55. We know N2 is equal to 1.6. And we know N3 is equal to 1.33. So what we know then is the thickness of this guy. So let's go to our thickness here. So my thickness was what, 288 or 285? 285. So the thickness of this guy is 285 nanometers. And all we want to know in this case then is what is the wavelength we're going to get, where this wavelength we want specifically in the visible light. So we're looking for some light which is in the visible light spectrum. So we talked about this before. Anybody remember what the visible light spectrum is? What's the range of wavelengths? So we talked about that when we first talked about light. It's what? Right, so it's a little bit less than that. So it's like that to what, about the size of a single cell organism, right? So in distance wise, remember how many nanometers? Well, 400 is in there. Good. So this is about something like 400 nanometers. Anybody know what the top is? That's it's about 800, 900, right? So we're going to say about 900. Okay? A little more than 700. So a little bit more. So a helium neon laser, for example, I think is about 740 nanometers. So a little bit higher than that, right? And that's the reddish color. So we'll say about 400 to about 900 nanometers. So all we're going to do is basically play the same game. We're going to calculate this for different n values until we get a wavelength in this range. That's basically all we're going to do. Now, difference here is that we do know the length, right? We know the thickness of this guy. We're just looking for him. So as we did last time, all we're going to do in this case then is we're going to count the total number of phase shifts so we know which one of those two expressions that we have to use, right? So let's do that. So here I'm going to go from a low index refraction to a high index refraction, which means do I get a phase shift? Yes. So in this case, this one is phase shifted. And now I'm going to go from a high index refraction to a low index refraction. So do I get a phase shift? No, right? So this one is not phase shifted, which means how many different phase shifts do I have? One, which means we're going to use the second version here. So we know our path length difference then is going to be twice the thickness, which is now going to be equal to n plus 1/2 times the wavelength divided by the index refraction of a second, which is then going to be n times lambda, the wavelength, times then the index refraction, or divided by, I should say, index refraction of the second one. Now, in this case, we know it's constructive interference, which means we're going to use this one now, right? So for this particular problem, our constructive interference will occur at 2L then is equal to n plus 1 half lambda divided by n2, or that means L then, or let's do it this way. We want to know what is the wavelength, right? So let's find this for the wavelength. So multiply here, divide by this guy. So my wavelength then is going to be the same thing as 2 times the thickness times the index refraction of the second, divided then by n plus 1. So this is going to be my wavelength. Okay. Again, lambda 2, or sorry, n2, we know is 1.6. We know the thickness is 285. Again, all we're going to do is plug in different n values until eventually we get a visible light spectrum. So let's do that. So in this case, we'll start off with n is equal to 0. So n is equal to 0. We are going to, after plugging in some numbers, we get that lambda 0 works out to be 1,824 nanometers. Is that between 400 and 900? Not exactly, right? So let's go to the next one. So let's do n is equal to 1. So lambda 1 then works out to be 608 nanometers. Is that between 400 and 900? Yes. So in this case, we know that our wavelength is going to be 600 nanometers, which means we're using the fact that what the two waves are a half, well, actually 3 halves wavelengths different from each other to give me this guy. What's up, Jaden? How do I know what? Oh, because in this case, again, I have to shift my wavelength because of my path length difference here. So this means that the distance that the one traveled versus the other one then would be 1 plus a half, which is then 3 halves, times the wavelength. So that means that the path length difference in this case, delta D, which means the distance that ray 2 traveled versus the distance that ray 1 traveled would be exactly 3 halves of the wavelength. Okay, so in this case, R2 minus R1 would be equal to 3.5 lambda. So that's right. So the total distance that this guy travels versus the other one then is 3.5 wavelengths in this case. And again, that half is there because they're out of phase with each other. So it has to move an extra half to get it to in phase to give me constructive interference. Everybody's doing okay? Not too bad. So thin films are not bad. And again, it's just applying this. But again, we have to remember, we have to count the total number of phase shifts because which one we use is going to be dependent on the number of phase shifts, right? So again, if we have 0 or 2, we use the usual. If we have 1, we're going to use simply this guy. Where again, the phase shifts come from if we have a low index refraction to a high index refraction. Other than that, so the rest of today, I'm going to sit up here and take a nap while you guys actually do work. Okay? That's great. So let's do that. I don't know what it was. I just could not wake up this morning. Must be all the darkness from the rain and everything, but whatever. Those are my problems, not your problems. So life will be great. So anyway, so let's look at wave interference problem. So here there's 2, so not too bad. So first one is we have a Snell's law problem. So this says that we have 2 different materials. So the one on top has an index refraction of 1.62. The one on the bottom one has an index refraction of 1.7. And the first one has a thickness of 2 centimeters and the other one has a thickness of 3 centimeters. And we're told is that what? Light is going to come in at an angle of 45 degrees relative to the normal line in this case. It's then going to refract onto the inside, travel some distance until it hits the next medium, refracts across that boundary where now it has a lower index refraction, which means it's going to bend away from the normal. And then it's going to travel the rest of the distance till it comes out through the other side. And then it's going to continue on its merry way. So what we want to know is what is the total distance that this guy travels going from where it entered into where it comes out, right? So yeah, over here, we want to know this total distance from here to here. Now, the easiest way to do this is to find, of course, this angle here, and then simply use geometry to find this distance here. We're going to call that D1. And then from here, I'm going to use, again, Snell's law to find this angle here. Use geometry again to find this distance. We can call that D2. And then the sum of D1 plus D2 is equal to the total distance of D. Right? Basic geometry with Snell's law. Okay. Second one now is thin film interference. So this says we have light, which is incident, again, pretty much perpendicularly. So again, it's close to the normal line. Onto material where the initial refraction of the second medium, so the one that's sandwiched in between the two, is 1.6, has a thickness of 400 nanometers. It lies between two other materials where initial refraction of N1 is 2, initial refraction of N3, again, is water, so 4/3 or 1.33. And then it says that the light is constructively interfering. So we want to know what wavelengths, again, within the visible light will give us this. Right? So for this particular thickness. In this case, it turns out there's actually two wavelengths that satisfy this. So one of them is 426.7 nanometers, and then the other one's actually 640 nanometers that are within that spectrum of 400 to say 900. So nice and easy, just perform the same thing we did here. Again, make sure you count the total number of phase shifts. How many phase shifts you have, that'll determine which equation you're going to use. And then pretty much just do it that way. So we have, 33 minutes left, 2 problems. So like I said, I'll pretty much just give you the rest of the time to work on these. They shouldn't take you that long, of course. Other than that, so the plan for tomorrow is we're going to start the last chapter tomorrow. The following Monday, because we only have Monday next week, we'll get most of the rest of that chapter done. When we come back after Thanksgiving, we'll try to get all of the rest of that chapter done on Monday. But if we only have a little bit left, we'll finish off the rest of it on Wednesday. Wednesday, we'll review for both the 5th exam and the final. Thursday, I'll give you off as long as we finish with everything. That way it gives you extra time to study and get ready basically for the 5th exam. Or if you're in a position where you don't need the 5th exam, you just want to say screw it, you can just say screw it. And then in that case, we'll have the 5th exam on Friday, and then the following Friday at the end of finals, because they love giving us either Wednesday or Friday. So in this case, the very last day of finals, we get our final exam. What's up? If you're in a position where you can, right? But if you haven't done so great on some of the exams and you need to make up those points, then obviously you'll want to take it. In those cases, probably. So if you're in a position where you don't technically need that exam, then yeah, I would say just do all the extra credits and then don't worry about the final. And again, the final will not involve anything from the 5th exam. So if you do decide not to take it, then you're hurt even less. Right. It will not hurt you in the long run. So that's right. So, was okay? Not too bad. What's up, Andy? Our 5th exam is Friday, and then the finals on the other Fridays. Okay, so the follow after that. So unfortunately, to get everything done in time, we have to have it on that Friday. So unfortunately, but I'm going to give the Thursday off, hopefully. Oh, one other thing I should mention too is that Thursday I will still be here. So if you want to come in and ask questions, whether it's homework or just, theory questions or anything like that, I will be in this room. I'll be hanging out here, maybe by myself, crying to myself, which will be great. But I'm sure somebody will come and bother me, so it'll be fantastic. So, but I will be here, so I will be here. Other than that, ask questions, life will be great. Give you time to work on those. And yeah, I'll turn this off because that's the end of what's going on.